Hi friends, welcome back on our YouTube channel. In today statistical mechanics, we are going to discuss about micro-canonical ensemble. We have already discussed about postulates of classical statistical mechanics. Now micro-canonical ensemble. So let's start micro-canonical ensemble. Here we will discuss about microcanonical ensemble. S is an extensive property and also about S satisfies the properties of the entropies required by the second law of thermodynamics. We have already know about the second law of thermodynamics. Now we prove that S satisfies the properties of the entropies required by the second law of thermodynamics. So first of all, microcanonical ensemble. It is a collection of essentially independent assemblies having the same energy, same volume and also the number of systems n. All the systems are of same type. The independent assemblies are separated by rigid, impermeable and well-insulated wall such that the values of E, V and N are not affected by the presence of other system. It means the energy, volume and number of particles always remain same. Now here we are showing a microcanonical ensemble. This is our ensemble and these are independent assemblies. It is clear from this figure that each assembly have the same energy E, same volume V and also the same number of particles or the same number of system N. We cannot actually specify the macroscopic energy of an assembly exactly. Now we consider two neighboring surfaces with energies E and E plus delta E. In macroscopic ensemble, every system has n molecule, V volume and energy between E and E plus delta E. Also, the average value of total momentum of the system is always 0. Now, here we are showing a two-dimensional phase space. We have two surfaces. This surface have energy E and this surface have energy E plus delta E. Let gamma E represents the volume in gamma space occupied by the microcanonical ensemble, and this is equal to integration E is less than H is less than E plus delta E. It means Hamiltonian lying between energy E and E plus delta E, D3 and P, D3 and Q. This is our gamma E, that is the volume in gamma space occupied by the microcanonical ensemble. Let sigma E represents the volume in gamma space enclosed by the energy surface of energy E. So sigma E is equal to integration E is less than H, D3 and P, D3 and Q, and gamma E is actually the volume occupied by the microcanonical ensemble in gamma space. So gamma E is equal to sigma E plus delta E minus sigma E. And what is this? This is actually the volume in gamma space enclosed by the energy surface of energy E plus delta E. If delta E is very much less than E, since gamma E equal to sigma E plus delta E minus sigma E and delta E is very much less than E, so gamma E is equal to del by del E of sigma E into delta E. Del by del E of sigma E is actually omega E. So this is our omega E. And therefore gamma E is equal to omega E delta E. What is omega E? Omega E is density of the system at the energy E. Since S is equal to K log gamma E, K is our Boltzmann's constant. So we have a relation S is equal to K log gamma E. Here S is entropy of the system and K is Boltzmann's constant. Now we will prove that S is an extensive property. If a system is composed of two sufficient large subsystems having entropies S1 and S2, then the entropy of the total system is given by S equal to S1 plus S2. Let a system is composed of two subsystems having N1 and N2 particles in the subsystems and V1 and V2 be the volumes corresponding to these subsystems respectively. It means the subsystem 1 have the number of particles N1 and volume V1, and the subsystem 2 have the number of particles N2 and volume V2. If H1 and H2 are the Hamiltonian of the two subsystems, then the total Hamiltonian of the composite system is H equals to H1 plus H2. What is H1? H1 is a Hamiltonian which is the function of P1 and Q1, and H2 is Hamiltonian. It is the function of P2 and Q2. So the total Hamiltonian of the composite system H is equal to H1 plus H2. Let the two subsystems be isolated from each other, and the energy of first subsystem lie between E1 and E1 plus delta E, and the energy of second subsystem lie between E2 and E2 plus delta E. Therefore, the entropies of the two subsystems are S1 equal to K log gamma 1 E1 and S2 equal to K log gamma 2 E2. S1 is the function of E1 and V1 and S2 is the function of E2 and V2. Here gamma 1 E1 and gamma 2 E2 are the volumes occupied by the two ensembles in their gamma space. So here we are showing a two-dimensional phase space. Limit of energy from 0 to E, and this is our surface E1 and this is the surface having energy E1 plus delta E, and this is our second subsystem. This is the surface corresponding to energy E2 and this is the surface corresponding to energy E2 plus delta E. So we consider two subsystems. First subsystem lying between energy E1 and E1 plus delta E. It means this is our first subsystem, and second subsystem lying between energy E2 and E2 plus delta E. So this is our second subsystem. These two diagrams represents the microcanonical ensemble of the two subsystems. Let the composite system be made up of two subsystems, and the microcanonical ensemble of it lie between energy range E and E plus twice delta E. Also, delta E is very much less than E. In the microcanonical ensemble of composite system, N1 particles whose momenta and coordinate are P1 and Q1 contained in the volume V1, and N2 particles whose momenta and coordinate are P2 and Q2 contained in the volume V2. Also, the energies E1 and E2 of the two subsystems satisfy the relation E1 plus E2 lying between E and E plus twice delta E. So, in the microcanonical ensemble of the composite system, we have these three conditions. Therefore, the total volume of the region of gamma space corresponding to 1 and 2 and energy lying between E1 plus E2 and E1 plus E2 plus twice delta E is gamma 1 E1, gamma 2 E2. For total volume of the ensemble, that is gamma E, we sum of gamma 1 E1 and gamma 2 E2 over E1 and E2. And for simplicity, we take lower bound for both systems to be 0 and divide each of energy spectra into interval of size delta E between 0 and E. So for simplicity, the lower bound of both systems has to be taken as 0 and we divide each of energy spectra into the interval of size delta E. Therefore, there are E upon delta E interval in each spectra. Now, gamma E is equal to sigma I equals to 1 to E upon delta E, gamma 1 EI, gamma 2 E minus EI. What is gamma E? Gamma E is the total volume of the ensemble. Here, EI is actually energy lying in the center of each energy interval. If the number of particles of the composite system N is equal to N1 plus N2, N1 is the number of particles in subsystem 1 and N2 is the number of particles in the subsystem 2. So if the number of particles of the composite system N equal to N1 plus N2 and volume of composite system V equal to V1 plus V2, also the entropy of composite system S is equal to K log gamma E. So we consider that the number of particles of the composite system N equal to N1 plus N2, volume of composite system V equal to V1 plus V2 and entropy of composite system S equal to K log gamma E. And gamma E is this one. So we substitute this value from here to here. So S equal to K log sigma I equal to 1 to E upon delta E, gamma 1 EI, gamma 2 E minus EI. When N1 and N2 is very large, it means N1 tends to infinitive and N2 tends to infinitive. Sigma I equal to 1 to E upon delta E, gamma 1 EI, gamma 2 E minus EI is equal to sum of E upon delta E positive terms. Because in this case, a single term dominates the sum. Let the largest term in the sum be gamma 1 E1 bar, gamma 2 E2 bar. So this is the largest term in the sum. Also, E1 bar plus E2 bar equal to E. So gamma 1 E1 bar, gamma 2 E2 bar is less and equal to gamma E is less and equal to E upon delta E, gamma 1 E1 bar, gamma 2 E2 bar. Now, we take the logarithmic of each side of this equation and also we multiply it with Boltzmann's constant K. So K log gamma 1 E1 bar, gamma 2 E2 bar is less and equal to K log gamma E is less and equal to K log E upon delta E plus K log gamma 1 E1 bar, gamma 2 E2 bar, because log of this term will be log E upon delta E, gamma 1 E1 bar, gamma 2 E2 bar, and this is equal to log of E upon delta E plus log of gamma 1 E1 bar gamma 2 E2 bar, and since we multiply this term with k, so we get this relation, or k log gamma E is less than equal to k log gamma 1 E1 bar plus k log gamma 2 E2 bar plus k log E upon delta E. We use here log m into n equal to log m plus log n, so we get this result. Since s equal to k log gamma E, so this is our s, this is S1 and this is S2. S1 and S2 are the entropies of the subsystem 1 and 2, and S is the entropy of composite system. So S equal to S1 plus S2 plus k log E upon delta E. S1 is the function of E1 bar and V1, and S2 is the function of E2 bar and V2. Since delta E is constant and it is independent of n, therefore log E upon delta E may be neglected. We already get this result. Therefore S is equal to S1 plus S2, and what is this? This is actually order of log n. Conclusion. Above result proves the extensive property of the entropy. The energies of the subsystems have the definite values E1 bar and E2 bar respectively. E1 and E2 maximize the function gamma 1 E1, gamma 2 E2 when E1 plus E2 is less than E. Also, differential of gamma 1, gamma 2 is equal to 0, or delta gamma 1 E1, gamma 2 E2 equals to 0, because for maximizing the function gamma 1 E1, gamma 2 E2, its first differential will be 0. So delta gamma 1 E1, gamma 2 E2 equal to 0. Also, delta 1 E1 plus delta 2 E2 equal to 0. Since delta gamma 1 E1, gamma 2 E2 equal to 0, it means delta of log gamma 1 E1, gamma 2 E2 will also be 0. So, on taking the logarithmic of this function, we get log of gamma 1 E1 plus log of gamma 2 E2, and its differential is 0. So delta log gamma 1 E1 is equal to minus delta log gamma 2 E2, which we written here. And from here, delta E1 equal to minus delta E2. Now, delta log gamma 1 E1 equal to minus delta log gamma 2 E2, and delta E1 equal to minus delta E2. So, del by del E1 of log gamma 1 E1 at E1 equal to E1 bar is equal to del by del E2 of log gamma 2 E2 at E2 equal to E2 bar. So, we divide this relation by delta E1, and this is with minus delta E2, and we get this result. Since S equal to K log gamma E, so this equation will be del by del E1 of S1 equal to del by del E2 of S2. Since S is this one, so del S1 by del E1 is equal to K del by del E1 of log of gamma 1 E1, and del S2 by del E2 is equal to K del by del E2 of log of gamma 2 E2. Now we transfer this K from here to here, and also this K from here to here. It means 1 upon K del S1 by del E1 equal to del by del E1 of log gamma 1 E1, and 1 upon K del S2 by del E2 equal to del by del E2 of log gamma 2 E2, which is written here. Now 1 upon K and 1 upon K will be cancelled out, and we get this result. Since del S by del E equals to 1 upon T, because dE equal to T ds by using second law of thermodynamics. So this will be 1 upon T1 and this will be 1 upon T2. So 1 upon T1 equal to 1 upon T2 or T1 equal to T2. E1 bar and E2 bar are such that the two subsystems have the same temperature, because here we get T1 equal to T2. T1 is the temperature of subsystem 1 and T2 is the temperature of subsystem 2. So E1 bar and E2 bar are such that the two subsystems have the same temperature. Thus, temperature is a parameter associated with the condition of equilibrium, and it is also related with energy. Thus, the proof of extensive property of entropy shows that temperature of an isolated system is the parameter representing the equilibrium between one part of the system and another. Since S equal to S1 plus S2 plus order of log n, and what this equation shows that, S equal to k log gamma e, S equal to k log omega e, and S equal to k log sigma e. All these three equations are equivalent up to the additive constant terms of order log n or smaller. So these three equations are same or equivalent up to the additive constant term of order of log n or smaller value. Now, S satisfies the property of the entropy required by the second law of thermodynamics. We prove this condition. In thermodynamics, the entropy is defined only for equilibrium state, and according to second law of thermodynamics, if an isolated system undergoes a change of thermodynamic state such that the initial and final state are equilibrium state, then the entropy of the final state is always not smaller than that of the initial state. It means the entropy of the final state will be greater than the entropy of the initial state, or it will be equal to the entropy of the initial state. Therefore, SF is always greater than or equal to SI. SF means entropy of the final state and SI is the entropy of initial state. It means entropy of the final state will be greater than or equal to the entropy of the initial state. Let N, V and E are independent macroscopic parameters of a system. If the system is isolated, the number of particles N and the energy are constant. Therefore, only volume can change. But volume cannot decrease without compressing the system or disturbing its isolation. So, the volume can only increase, it cannot decrease. Therefore, second law of thermodynamics states that entropy S is a non-decreasing function of volume. Therefore, entropy defined by any of the following equation represents that S of a system is a function of volume V and internal energy E. Since S equal to k log gamma E, S equal to k log omega E and S equal to k log sigma E, this represents the connection between the microcanonical ensemble and thermodynamics. Here we end our session. In today's session, we have discussed about microcanonical ensemble. Goodbye.